Good day, everyone. Today we explore the chapter 4 for the IPS entitled Industrial Power Quality, and we look at the outline for chapter 4. 4.1 is regarding to the motor starting study. 4.2 is about the applications of the industrial power factor correction, and 4.3 is on the harmonics treatment in the IPS, and 4.4 is the voltage sex analysis, and finally we explore a little bit on the flicker analysis in the IPS. And we try to refresh for the motor starting study in the IPS, and because we know that the IPS having several types of the motors, especially for the induction motor, and the starting methods will reflect to the power quality that it will be faced in the IPS. So that's why we try to explore on the starting methods, and then we deal it with the power quality issues on the motor starting. So we look at the starting methods. We have various type of the starting methods available. For example, the direct online or DOL. We have the star delta connections of this starting method, and the part winding. This is quite rare to be used in the IPS. Rather, the resistance stator also is quite rare to be used in the IPS. Auto transformer, yes, it is quite frequent used in the IPS, and the slip rings motor is especially for the wound rotor motors only, and the soft starter as well as the frequency converter. These two are very common used in the IPS nowadays, especially for the frequency converter. And we look at the review on each of the starting methods. We start from the DOL, the direct online startings. So implied by the name direct online means we will start our motor, especially the induction motor, directly. That means we have the switch here, so that means we just switch on the switch directly to this particular motor, and we start it on that. That means we start this motor using the full voltage starting. So that means once we switch on the switch to the motors to run the motors, that means this motor will receive a full voltage at the beginning of their starting. So that's why what we can expected from this DOL method of the starting is the current. The starting current is very high, so the current on the starting is about 5 to 8 times of the rated currents. So this is the disadvantage of this of the DOL as compared to others. And at the same time, the torque on the starting also is quite low, from 0.5 to 1.5. That means we cannot expect a high starting torque by using the DOL, because the starting torque is only 0.5 to 1.5 at the rated torque. RT is the rated torques. So you can see the performance of the DOL startings by the illustration here. The illustrations, this is the current, the starting currents, and this is IN is the nominal currents, the nominal currents. So you can see the huge increments during the starting. Okay? So for the DOL is 5 to 8 times. That's why for the DOL starting, we just implement it for a small motor, say below 5 horsepower motors. And above 5 horsepower, then we use alternative methods to start it, just to reduce the starting current, because the starting current is very annoying in the IPS. It will cause a lot of problems, especially the switching elements. So it will disturb your switching element as well, and it will introduce the transient as well. There's a lot of unwanted power quality issues will come in by the starting method of the motors. So for the star delta, this is quite famous in the IPS, especially for the medium size of the motor. So beginning, it will start using the star connection. That means the windings of the motors is connected in star. Is connected in star with the system. So this is the star connection. Then after we connect in the star connections, after several times, so for example, we can monitor the speeds of the motor. So once it reach half of the speeds, half of the rated speed, then we can switch this KM1 to KM3. So they mean by switching on the KM3, now we are in the delta connections, in the delta connection. That means we switch from star to delta connections. So why we start from the star instead of the delta? Because in the star connections, we know that the voltage is divided by Z3, the Z3. So that's why once the voltage is lower, then we try to reduce the current peak during the starting, right? And what we expect, the starting current is about 1.5 to 2.6 of the rated current. So it is much lower compared to the DOL. And for the torque, the starting torques, it is very low, 0.2 to 0.5 as well. Okay? So that means what the intention of the star delta is, we start with the lower voltage. Then after that, when our motor is driving at about half of the rated speed, then we only switch to the full voltage applications. Okay, so that is the intention of the star delta. And of course, for the starting of the motor, these two is our main concern. One is the starting current, and another one is the starting torque. Because in some application in the IPS, we need a high starting torque, especially the cutting machine, for example. So we need a very high starting torque, especially those cutting the metal. Okay? And come to the this is quite rare, the part. I mean, we just take a part of the winding, a part of the standard winding, and then we start it with that. It is very rare to be used in the British standards IPS. Okay, so it's rather more to the Northern American. That is the Americans markets. It is more to for the American markets. And for the resistance also, the resistance at the stator starting, so we put extra or additional resistance just to limit the current, just to limit the current, the starting current. So that's why in by limiting the currents, so of course we have the voltage drop here, and when we have additional resistance to be placed series to the stator during the starting, then we will experiencing the so-called the power losses as well, right? The power losses here. So that's why this type of the starting method is not so familiar or so famous in the IPS, and because of the power losses, and because of the extra power losses. So of course, once it reach a certain speeds, once it reach a certain speed, and then it will switch off or isolate the additional resistance here. It is not continuously run with the resistance, but rather it will cut off the resistance, and it will continue run like the DOL. And what we expect is the short circuit, the starting current is 4.5 of the rated current, and the starting torque is 0.75 of the rated torque. And the auto transformer, so the next is the auto transformer. So we use one special transformer. So that means this transformer we can adjust. We can adjust how many percent we wanted to start the motor. And I mean how many percent of the winding of the auto transformer. So we can tap it. It seems like we have the tapping, so we can tap it. For example, we have few steps here. So during the step 1, so we tap at the lower percentage of the winding. That means we just switch on uh, or the start the motor with a partial of the windings of the transformer. That means we reduce the voltage. Yeah, we reduce the voltage, and come to the certain, especially this is the n is the speed, the speed in RPM. So as we can see here, so once the speed is come or reaching to the 50% of its nominal speeds, that means we can switch to another steps. Yeah, we can switch to another step like this one. So step 2 and step 3. So it seems like we can play around with the tapping. So the starting current is about 1.7 to 4 is quite okay, quite nice, and the starting torques is still low, 0.5 to 0.85. And the slip ring is only applicable for the wound rotor, and the wound rotor types of the induction motor. So this is quite rare, because most of the industrial application we use the so-called the induction is the non-slips. It's the non-slips motor, and normally what we use is the non-slips motor in the industrial applications. And the soft starter, so if you are using the soft starter, that means you can ram the starting current, just ramping it, ram from 0, slowly go up to the maximum current, or you can control it by the voltage. Slowly you ram the voltage. That means we start from 0 and slowly we increase the voltage, ramp the voltage up to the maximum voltage. And with this kind of the starting method, we estimate that the starting current will be 3 to 4 times. And this control is especially suitable for the turbo machines. And for example, you have the centrifugal pumps and a fan as well. So this is quite suitable for this type of the application. And finally, we have this is very popular these days. We use the frequency converter starting, and that means we have the rectifier. Everything we control in the DC modes. So that means from the DC, then we can have the PWM, and we adjust the frequency. So when we adjust the frequency, we adjust the voltage. Okay? So this is the frequency that means frequency related voltage, frequency based voltage control. Okay? So with this kind of the starting, that means we can start our motor with a very soft manner, so it has a starting with high inertial loads. This is what we want as compared to others. Because by using the frequency converter starting method, so we will expect high initial loads. That means high starting torque. We can have the high starting torque and low starting current. So this is what we want from the starting method. Okay, this is the summary. So you have the direct online, star delta, up to the frequency converter. Then you can see the motor type and what is the power factor, and then about the thermal stress. Then you can look at the recommended types of the load as well. So for example, in the frequency converter, so it stated here is high number of starts available. That means you can start that means unlimited times of the startings. Okay? And what about the power factor? Power factor, if you use the frequency converter, is very high. And what about the voltage and current harmonics? So current and voltage harmonic is also high. So this is the disadvantage of this starting method, because it will introduce the harmonics to our system as compared to especially the slip ring here is very low. Okay? And what about the voltage dip? Once we start our motor, so of course the motor will draw so much starting currents, and then at that particular time our voltage will be deep, or will be sag, and that means the voltage will be reduced. So it depends on which type of the starting method you use. So if you wanted to have a low voltage dip, that means you have to you can choose for the frequency converter, for example the soft starter, or even the slip ring here. So if you are using the wound rotor types of the induction motor, so you can see through the available torque also. The available torque, for example, so it's 1.5 to 2 is good enough. It's good enough for the industry application, especially that need the higher starting torque. So 1.5 to 2 of the rated torque. So if the initial torque is 0.2 to 0.5, that means it's considered very low. It's very low. And what we can expect from the motor startings regarding to the power quality. So first you will incur the voltage drop or voltage dips. Okay? Once it draw so much starting current, then our voltage will experiencing some dips. And of course the inrush current, we can avoid the inrush current, or sometimes we call it as a transient, and the transient currents. And the voltage of current harmonics also, especially when we use the converter types of the starting methods, like the frequency converter start. And the voltage flicker, so it depends on the starting method as well. Okay? Because the voltage flicker is much depends on the frequency change. So especially when you use the converter to change or to switch to one and another, that means you change the frequency, so of course it will cause the voltage flicker also. So there is one simple example here. So we try to understand about the voltage drop during the motor start. So here we have the supply here. So we supply to a motor 75 kilowatt of the motors at 400 volts. Okay, so the power factor during starting is 0.3, and the SOC, KSOC is the coefficient or the constant, the constant during the starting. So that means how many apparent power it requires during the starting. So it's stated here 7 kVA per kilometer, so per kilowatt, sorry. So that means it requires 7 kVA of apparent power per kilowatt of the motor. So in this case we have 75 kilowatt, that means we multiply with 75, then we know how much is the apparent power is required during starting. Okay? So this is only during starting. Okay? So in this case what we have limited is the power factor. We have limited the power factor, maximum is only 3%. So that means at PCC here, the point of common coupling here, so the voltage drop during the motor starting is allowed only 3%. Then we have the ZS, we have the impedance for the source there, the incoming source, the supply. S is the supply in milliohms here. Then we have the transformer to step down from 11 kV to 400 volts. The rated size is 1 MVA, and percentage of the impedance is 5%, and X over R ratio is 5. So why we need the X over R ratio? Because with this ratio, X over the R ratio, the X is the reactant and R is the resistance. With this, then we can know the power factor angles. We can know the power factor angle because X over R is equal to the tangent theta. Okay, now we see the solutions. As I told you just now, we need to analyze how much is the apparent power during the starting. SS is the apparent power. 7 times 75 is 5 to 5 kVA. Okay, So it's 5 to 5 kVA from these coefficients. C is the coefficients. And the motor impedance during starting. Okay, we analyze the motor impedance during the starting, because during the motor starting, or when you deal with the voltage drop, the first thing you need to find is the impedance, all the way from the supply to that applications. Let's say in this case, the application is only the motor, so that means we need to find the impedance from the starting here, the supply, up to the motor point here. And that means what we need is it has been given the impedance of the ZS here, then what is the impedance for the transformer, then impedance for the line, this is the line, the cables, and what is the impedance for the motor as well, okay, during the starting. So Zm start is the mode during the motor starting. So this is the impedance of the motor during the starting. So it's very simple, V square over S here. S is the starting apparent power, so V is 400, and then cos theta we can find it from here, because it has been given the power factor during starting 0.3. So cos theta is the power factor, which means 0.3 plus the sine theta. Of course, we need to find the theta in order to find the sine theta here. So the sine theta is 0.954. So all in here we have 91 plus J 290 milliohms for the Zm start. And what about the voltage at the PCC? So the voltage at the PCC is the ratio of the impedance, the ratio of impedance 1. So the impedance of the motor plus the L, so that means up to the PCC here. Okay, so that means from here, this point, up to the motor, that means we have two. We have a ZL plus the Z motor starts. Okay, and we need to compare it with the that means the ZPCC. ZPCC means is before the PCC. Okay, that means the impedance before the PCC, which is the ZS plus the Z transformer. Okay, so that is the ZPCC. ZPCC is the ZS plus Z transformer. Okay, then we multiply with the Vn. Vn is the 400, as stated here, is 400 volt. Okay, now we look at the Z transformer. So how we find the Z transformer? This is 5% just now. So it's has been given here is 5%. The Z percentage is 5%. So that's why we use it 5%. 5% in per unit. We written it in per unit, and then it's a V square over S. V is the voltage of the transformer, the secondary, and of course we are interested the secondary voltage. It's not the primary, because our motor is installed at the secondary, it's not primary. So if our concern is at the primary, of course you can change it to the primary, but this times what we consider is only the secondary application. So it's divided by 1 MVA, and then this is the cost 78.69 is you have to find it from the X over R ratio here. As I told you, the X over R ratio is equal to tangent theta. Tangent theta. So tangent theta, then you can find the theta for that. After that, you use that theta to find the cos theta here. And the cos theta. So in this case, the theta is 78.69. Okay. And then finally, we can obtain the Z for the transformer and the Z for the PCC as well. Okay, the Z for the PCC as well. That means we just add the Z transformer plus the Z for the source, and then we can find for the Z PCC. And after that, we simply calculate for the voltage at the PCC point, and the voltage 400 divided by this is the ratio that we wanted. And finally we obtains the voltage at the PCC during the motor starting is only 389 instead of 400. So how much is the voltage drop? Is 400 minus the the voltage at the PCC divided by the standard one is 400 times 100%. That means we know that the voltage drop during the motor starting is only 2.64%, so which is not exceed the limit of 3. So that means we can continue to install this motor. So this is how we calculate for the motor starting, especially the voltage drops. And now we shift to the power factor in the sinusoidal. Right? We have sinusoidal conditions and the non-sinusoidal conditions. So of course sinusoidal condition is the ideal conditions, the ideal condition, while the non-sinusoidal condition is the non-ideal. Non-ideal, that means we have some disturbances, for example from the harmonics. Okay, that means our system's waveform is no more the sinusoidal, but it is non-sinusoidal. Okay, we look at the power factor. The power factor, how the power factor is look like in the sinusoidal condition. I mean in the ideal conditions. We have the R, then we have the motors, then we have the motor load here. The motor load also in the linear condition. It's a linear. That means when you plot the graph, the R and X, and then it will produce a linear, and that means straight line. Straight line. That means we have a very basic one. We have the V and the voltage and the currents. The voltage and current. V1 is the V peak. The V peak for 1. I is the I peak. So of course it is a sine wave, sinusoidal. And we have the del 1. Del 1 is the angle for voltage, and theta of course is the angle for the currents. So what is the power factor? The power factor angle is actually the delta 1 minus the theta 1. So that is the normal power factor angle. Okay, and the true power factor is the real power factor. The real power factor is equal to the P average, divided by S. S of course is the V RMS multiplied with the IRMS, and the P average is how much is the P average here. Okay, the P average. Okay, for the purely sinusoidal case, we still deal with the purely sinusoidal. Okay, and then we look at these statements. The true power factor is equal to the displacement power factor. What is mean is the displacement power factor is the that mean when we take the angle of delta 1 minus delta 1 theta 1, delta 1 minus theta 1. So this is the displacement power factor. That means we just consider for the fundamental. And I mean in the harmonics we have fundamental waveforms, then we have the second order, third order harmonics, and etc. So that is the remainings of the harmonics contents. But in the displacement power factor, we only deal with the fundamental only. Okay, that means the V1 and I1, and what is their angle. That means the V1 angle is del 1, and the I1 angle is the theta 1. Okay, so the difference between the these two angles are the power factor angle, and the power factor is the displacement power factor. It is not the true power factor, but of course in the sinusoidal case, true power factor is equal to the displacement power factor. Later we can see the difference in the non-sinusoidal case. Okay, so it is totally different. And of course we can use back the power P average divided by so this is the S, the S. Okay, and then we can substitute in terms of the voltage and currents. For the P average is the V1, and V1 is the peak. Peak divided by Z2 is become the RMS, VRMS and IRMS, and cos this is the power factor. This is the displacement power factor angle. And of course the S is also the R, VRMS and IRMS. Okay, that means when we cancel out this and this, then we only remain for the cos theta 1 minus theta del 1 minus theta 1. Okay, so this is the displacement power factor. That means displacement power vector means is the common power vector that we understood, and that means it's only considered for the fundamental waveform. Okay, this is the illustrations about the effects of the power vector on the power losses. So let's say we have a power factor 1. So of course the power losses is very small, just 1 only. So when we reduce the power vector, let's say to 0.5, so you can see the increment of the power losses. I mean, when you have more power losses, mean our system is inefficient. It is inefficient with a lot of the losses, a lot of losses rather than the power that we can use for running the motor. Okay, so power losses is just a waste, as the, for example, as a heat, as a noise, for example. Okay, this time we reach to the non-sinusoidal. So this is the real case in the industrial power system, because in our industrial power system is normally is non-sinusoidal condition. Is no more sinusoidal. Okay, for the non-sinusoidal, of course, we need to include all the harmonics content, all the harmonic contents, rather than just we focus on the fundamental of the waveform. Okay, so of course we have to use the Fourier series to represent the harmonic content. For example, the Vt here is the summation of the Vk. So k is from 1. 1 of course is the fundamental. The fundamental is 1 and up to infinity. So it depends on how much, how many harmonic order we need to identify. But following the standard IEEE standard, the harmonics that will give significant impacts to our industrial power system is up to only 31 only. And that means the maximum harmonic order that we consider or on our consideration is only up to 31 of the harmonic order. Okay, so the rest, that means above 31, it is considered very, very small, and it won't give any impact. It won't give any significant impacts to our system. Okay, so this is the same things, and that means we need to sum all the elements. We need to sum all the elements from k to 1 up to let's say k31. Okay, that means we need to all to sum it. And same to the current here. Same to the current here. Of course, our concern is the theta, the del, and the theta here. Okay, and VRMS. So this one is in the VRMS. VRMS, because the V square, and then you divide by Z2. Actually, this is Z2. Okay, Z2, and then also of course we can write it as a VKRMS square. So that means we RMS, we take all the RMS in all the harmonic order. So let's say we have harmonic order 1, of course is the fundamental, harmonic order 2, 3, 4, and etc. Okay, that means we just square it, and then after that we square root it again. And the p-average is the summation of the multiplication of the V RMS and I RMS with the consideration of the cos theta here, and the cos power factor angle. Okay, so that means we have so many. So P1 average is the fundamental waveform, P2 is for the second order harmonics, this is third order harmonic, and etc. Okay. And then the total harmonic distortion or the distortion factor. Okay, so the THD for the voltage, THD for the currents. Okay, so how it's been calculated is that means we square root all the summation for the V square. Okay, for the V square, that means in these times the K is starting from 2. That means it is not counting the fundamental. Okay, because the fundamental is our reference here, and the fundamental is our reference. So in order to calculate the components of the harmonics only, so that means we start with K2. Okay? So K2, K3, K4, and etc. Yeah? And then we multiply with 100%. So it will be represented in the percentage. Okay? then of course it can be written like this one. V1 is the fundamental, and this is the rest. I mean, besides the fundamentals, harmonic contents. Okay, and same to the current here. And of course the VRMS is equal to the V1 RMS. That means you can manipulate this, and finally you can obtain this. Okay, the VRMS equal to the V1 RMS is the fundamental RMS, and then you multiply with the square roots 1 plus THD, and this one is in percentage. Let's say the THD for the voltage is, let's say, 5%, so that means we just put 5 here. 5 divided by 100% here, and then square it. Okay, so same to the current here. Okay, then after that we can find the true power factor. This time the true power factor is no more equal to the displacement power factor. It's totally different. Okay, it is lower than the displacement power factor, and because we have included the harmonic contents, okay, in the true power factor. So in the true power vector, the calculation is still P average, and the P average we can calculate using the this one, using these equations. Then after that, the V, that means this is the fundamental for the V, fundamental for the current, and then how much is the THD, the total harmonic distortion for voltage, and total harmonic distortion for the currents. So this is how we calculate. So we can look at this issue in a clearer manner by exploring the example 4.2 here. So we have the frequency 50, 150, 250. Of course 150 is the third order of the harmonic, and divide by 50, then we have 3, 5 and 7 order of harmonics. Okay, so this is the voltage. This is for the fundamental. Of course 50 Hertz is the fundamental, so at the fundamental we have 415 volts, and the current is 50. This is the angle. The angle is very important. Okay, and this is the voltage at the third order harmonics, and fifth order harmonic, and seventh order of the harmonics, and etc. Same to the currents. Okay, so that means with these applications we need to find how much is the true power factor for this application. So let's check for the THD. So of course we begin with the THD for V and I. Okay, so for the voltage we have the we start from the second one. The second one is the third order, fifth order and seventh order. Okay, so it is 9.5, 5.8 and 1.2. so of course we have put in here 9.5 square plus 8.5 square plus 1.2 square, and then we square root it, divide by 415. Okay, so divide by the fundamental, and this is the fundamental, and we obtain is 2.7% only for THD V. THD I is 31.76%. So this is not allowed. Right? This is normally not allowed by the standards. It's too much, 31%. And the P average, how to find the P average? P average is the that means with the summations of the V and I cos del here. Okay, that means we start from the K is equal to 1. K is 1 is the fundamental. So this is the fundamental 415 multiplied with 50, and multiply with the 50 is the current, fundamental current, fundamental voltage multiplied with fundamental current, and then cos theta. This is the del minus theta. Right? Del minus is because del here we have 0 minus 30. Yeah? Because minus become positive. Yeah? Minus become positive. Negative become positive. That's why we have 0 plus 30. So same to the rest here. Okay, so this is the third order harmonic, fifth order and seventh order harmonic. So finally we sum it, then we obtain 18,000 watts. Okay, 18,000 watts. And with that we can substitute in our equation just now, and we have this equation. So this is the P average, so this is the VRMS, V1 RMS and I1 RMS. Okay, so this is the fundamental power, P, fundamental P, and this is the average P, after consider the harmonic contents. So why it is lesser than this one? And by right, if you include you add the harmonic content, it should be more than this one, right? Because the angle, because of the angle here, because some is the plus positive leading and some is the lagging. So that's why you will when you add up this all, then it we realize that it is smaller than the average here. Okay, and we just put in 2.7% here and 31.76% here. And finally, we got the true power factor is 0.83 as compared to the displacement power factor. The displacement power factor, that means we only consider for the fundamental, which is cos 30, which is cos 30, this one. Okay, cos 30, it is 0.866. Okay, so that means there is the difference between the displacement power factor and the true power factor in this case. Right. Then this is the effects again, right? This is the linear loads. Just now we have the linear loads, and this time we have the non-linear load. Of course, the power losses impacts is much higher than the linear loads when you decrease the power factor. Okay, this is the applications of the a motor. So we have one motor. It require P, Q1, and the S1. Okay? So it's the Q1. So where it obtain the Q1? So actually the Q1 it obtains from, one is the supply, the Q2 here, and plus the QC. QC is the compensate reactive power supplied by the power factor corrector or the capacitor bank here. Okay, so they mean Q2 plus QC is equal to the Q1 here. Okay, so that is our consideration, the red color one. Okay, then we look at the phasor diagram here. The phasor diagram is stated here the IR. IR is for the P, the IR, and this one is the Q1. Q1 is before the compensation, then before we correct the power factor. And so this is this much is our Q1. That means the real the reactive power required by our motor is this much. And after that we compensate with the QC. Then C is the compensate. So that means we top up with the QC here. Then that means we reduce the power factor angle from theta 1 here. Then we reduce to 2 here. Okay, and same to the currents. That means we reduce from I1 to I2. I1 is compared to I2. Of course, I2 is shorter than I1. Okay, that means we have saved some currents for that. And same to this one. This is the triangle, a power triangle. So we have P, and then we have original. We have this much. We have this much of the Q1. It is required a Q1 here. Okay, this much. And then we have the Q2. This is Q2 after we correct it using the QC here. Using the QC here. So this is how we utilize the power factor corrector to improve the power factor. Okay, so this is the application, one of the applications of the power factor corrections. Okay, now we look at the power factor value for some applications in the IPS. So let's say we have the common induction motor. We have the common induction motor. So it's depend on how much you load it. Okay, so that means if your loading for the induction motor is 0, so that means you will experience very low power factor. That means when you gradually increase the loads, that means the shaft. So shaft will drive the loads. For example, the conveyor. So we use the induction motor to drive the conveyor, the belt. So once we increase the load or the torque at the induction motor shaft, let's say up to 75%, now we can increase the power factor, and the power factor to 0.8, for example. So the common one is 0.85 if you reach the 100% of the loading. So this is the rest of the equipment or the devices that we use. We commonly use in the IPS. For example, the ovens, and the oven is one, of course it is a heating element, and it only use the resistance, it only use the resistance is one. And then the arc welding, arc weldings, it is about 0.7 to 0.9. If we are still using the fluorescent lamp, so you can experience from 0.5 to 0.93. So this is after we compensate it. And normally in the production line we use the discharge lamp, and the discharge lamp, so you can experience very low volt power factor is 0.4 to 0.6. So nowadays we have tried to replace the discharge lamp for the LED applications. And why we need to improve the power factor? Of course, it's very obvious. We can increase the power available from the incoming. Let's say we have the 100, so we can use this 100% for the rest of the loads. If we have a pure power factor 1, so let's say our power factor is 0.8 only. So even though we have 100, but what we can use is only 80% of the power. Then I mean we have 20% of the losses. We have 20% of losses, and then reductions of reduce the voltage drop also. Okay, so once you increase the power factor, of course your current is minimized, then you can minimize the voltage drop as well, and then of course the losses also. Okay, and of course when you have a smaller current, then your cable size also becomes smaller, and then your cost of the installation also becomes smaller. And then one thing is the agings of the cable also will be enhanced. Okay, and then last one is of course in overall, so it reduce our electricity costs. Okay. And in IPS normally we have two types of the capacitor bank for as a power factor corrector. One is fixed capacitor, so it's depend on how we utilize it and where we utilize the power factor capacitor. Okay, so I try to check the recordings. I just wondering whether it's recording or exit. Okay, it's okay, no problems. And is a fixed capacitor normally we use at the terminal of the inductive device. For example, we have motor, so we just place the fixed capacitor at the motor terminal. Okay? Or at the bus bar, we're supplying the numerous small motor, so that means the fixed capacitor is normally for small applications, small load applications. Another one is in case where the level of load is reasonably constant, so that means our load won't change too much. In that case you can use the fixed capacitor. Otherwise you can choose for the automatic capacitor bank. That means you have the switching, and you have the switching some sort like you have the voltage taps, but this time it's not the voltage tap, but it taps the Q. And that means when you tap from switch 1 to switch 2, that means you will increase the Q that injected to our system. So normally it has a 6 switching, and it has 6 switching or 12 switching, so it depends on the applications. It's normally is for the heavier loads, then we use the automatic capacitor bank. So for example, we can place it at the feeder, at the main switch gear there. Okay? Then we can control the entire flow of the reactive power. Okay, these are some of the steps that you required to improve the power factor. Okay, the first one is you need to identify what is the total system loading, okay, in terms of the P and Q, and then what is the frequency and the voltage for your system, as well as your capacitor. When you purchase the capacitor, of course the voltage is different and the frequency also different as compared to our system. Let's say our system is 400 volts, so your capacitor you purchase must be higher a little bit. Let's say 525 volts. So of course it has a fixed value for the voltage and that to be purchased. It's some sort like you buy the resistor. right? So of course you cannot simply choose for the value. Of course it has the a fixed value. So same to the frequency and the voltage for the capacitor. And of course after that you need to analyze what is the overall power factor and what is our targeted power factor. eh? So let's say overall power factor is 0.6, then our targeted is we need to correct it to 0.9, for example. Okay, and the next steps will be the capacitor sizing, right? How to calculate the sizing. So the sizing is depend on harmonics content also, right? It depend on the harmonic contents. That's why the capacitor voltage must be higher, always higher than the system voltage. So this is the requirement, especially dealing with the harmonics. Okay, and the frequency also. Frequency is also a little bit higher than the system. And then we can calculate for the how much is the compensated Q, the compensated reactive power that we required to increase from the overall power factor to the targeted power factor. Okay. Now after that we try to analyze. After we have the capacitor bank in place and everything is okay, then another issue of the power quality when you install the capacitor bank is the resonant effect and the switching transient as well. So these are two main impact. Beside, of course, we are happy when we increase the power vector, then let's say from 0.6 to 0.9, for example. So we are happy on that. But at the same time, we need to check for another two possible issue of the power quality, which is the resonant effect and the switching transient. Okay, in the commercial calculation, normally we don't ask the engineer to calculate one by one. Of course, they will utilize the a table like this one. They say this is your plant original power factor, and this is your desired power factor. So let's say you correct from 0.52 to 0.88. So how much you require the Q? So this is the K factor, so called the K factor. Okay, the K factor. So the K factor, once you have the K factor here, from 0.52 to 0.88 here, so this is the K factor that you required, and then you just simply multiply with your plant's total P, and then you know how much is the compensated Q you required. Because the compensated Q, as we seen just now, is Q1 minus Q2. Okay, Q1 is our that means that before you compensate, before you compensate, and this is after you compensate. Then how much is the Q that you can draw from the system? So this is from the system, and this is from your loads. This is from your load, and this is from your system. Of course, this one is from the capacitor bank. Capacitor bank, and we know that the tangent theta is equal to the Q divided by P. Tangent theta is equal to the Q divided by P. So using this concept, then we have this K factor. Okay, so Q over P. Okay, because tangent theta is equal to the Q over P. So Q is equal to the P multiplied with the tangent theta. So the tangent theta also we have to extend, because we have Q1 minus Q2 here. So the Q1, of course, we have the power factor angle. So this is the power factor angle 1. Okay, this is the power factor angle 2. So tangent power factor angle 1 minus tangent power factor angle 2. Okay, and then you can use the Excel, for example, just to have the so-called the compensated Q or the K factor. And just now we said that the voltage for the capacitor or the frequency for the capacitor must be a little bit higher than our system voltage, and this difference will also give impact to the Q. That means how much is the Q when you purchase the capacitor bank. It has written the Q in kVAR. How much is the kVAR for the capacitor bank? Okay, and it also will give impacts to the Q that injected to our system. So this is two different things. So one is the stored Q, and I mean the stored Q in the capacitor bank, and we call it as a Q cap. Q cap is the reactive power inside the capacitor bank itself, and the QS is the effective reactive power that injected into the supply. So it depends on the V cap and the Vs. So V cap is the capacitor voltage. So how much is the capacitor voltage? And the Vs, of course, is our system voltage and the supply voltage. And same to the frequency here. Okay? So that means, let's say what we need, let's say we need 100 here. So 100 here. So how much we need to purchase of the Q for the cap here. So it depends on this variable, this variable V cap and the Vs here. So for example, here you have an incoming 3-phase 50 Hz 400 volt here. So we have a capacitor bank 1 C1. So we have a power factor corrector C2. This one is purposely treated for the M1 application only. Okay, this was for M1, and this one is for the bus bar. So that means this power factor can correct the entire load for this bus bar. As long as you connected to this bus bar, so this power factor will correct the power factor, especially for this entire bus bar. Okay? And M1 is the motor number 1, motor number 2. So you have lump load 1 and lump load. So lump load, of course, is defined here. Okay? So M1, okay, you have the 8 units of 3-phase induction motor. So each one is 2 kVA, then rated at 0.78 power factor lagging, okay, with efficiency 88%. So M2 is consists of 24 units of the single phase conveyor motor, so connected in the 3-phase, and each one is rated at 300 watts, 0.82 lagging power factor with efficiency 78%. So the lump load is the rated at 10 kVAR, 10 kVAR, and 0.9 lagging power factor. And what about the power factor corrector C1? It has a 6 steps. That means you have 6 steps, 6 steps to be switched. You can switch 6 steps of the power factor corrector. So it arranged like this one. 1, 1, 2, 2, 4, 4. That means 1 here is the 1 units. So how much is the 1 unit? It stated here. The unit capacitor used is rated at the voltage for the cap is 525, as compared to the system is 400. And then 1 unit of the capacitor switch here, 1 is 2 kVAR. So of course, when you switch to step 1, step 2, step 3, so that means when you switch to step 3, that means you have 2 plus 1 plus 1. Okay, so that means total is 2 plus 1 plus 1 is 4 units. So 4 units times 2 kVAR. So that means you have 8 kVAR when you switch to step 3. Okay, so that means you can calculate that way. So it depends on how much is our system required. Okay, so the minimum is just step 1, only 1 kVAR. Okay. So of course, by using this analog, we can call it as an analog switch like this one. So it might cause the overcorrectors. It might cause the overcorrectors. So it depends on your design. So that means you have to design it wisely. That means you have to calculate it. How much is your system need, and what is the minimum size of the unit capacitor. Okay. So let's say our system is just required to compensate the reactive power for, let's say 1.2 kVAR. But now when we switch to step 1, so it will give you 2 kVAR. So that means it is over corrected. Then the overall system power factor will become leading in that case. So that is we as an engineer, we need to consider these things. So the C2 is only have 3 steps of the power factor corrector is 1, 2, 3. Okay, so the units capacitor we don't know. Okay, we don't know. We only know it is rated at 440 volts only. Okay, then we have to analyze the average power factor of this factory. Okay, when both C1 and C2 are disabled. Okay, so how to calculate it? So I have the solution here. So when C1 and C2 are disabled, so that means we can calculate that we have three types of the load here. Okay, so the M1, M2, and the lump load 1, okay, L1. So this is we have considered 8 units, or consists of 8 unit of the motor, and that means in M2 we have 24 units, and of course this one is for the L1. Okay, so let's say we go for the 8 units. Each unit is 2 kVA, and so this is the power factor. Okay, this is the power factor is 0.75, and plus, in order to find the P and Q here, so Q is the sine theta. Okay, sine theta is the up cos 0.78 here. Okay, then same to this one, same to this one. It has been given our M2 is each one is consists of 300 watts here, 300 watts, and of course we can use this P to find the Q, using the tangent here, tangent theta. As I told you, tangent theta is equal to the Q over P. Tangent theta is Q over P. And then this one is given the 10K also, the 10K. So we can use this 10K of the kVAR, because it only gives us the 10 kVAR without giving the P. So then we can use the same concept, tangent theta is equal to the Q over P. We can find for the P here. And all in here we have the P plus JQ, and this is for the system and the total. So that's why we can simply analyze the power factor, the cos up tangent, because tangent theta, theta is the power factor angle. Tangent theta is equal to Q divided by P. So Q divided by P, and up tangent, of course. Okay, so that's why the cos theta is equal to 0.845 lagging in this case. Okay, and then the second question is recommend the proper kVAR rating for the unit capacitor. Just now, because we see the C2, we don't have the unit capacitor. Okay, that's why it required us to calculate. So how much is the proper unit capacitor to be used? So the conditions given here is the M1 to be corrected at least to 0.95. So that means M1 motor is corrected to 0.95. Okay, so we assume C2 is switched to step 3. So that means when we switch to step 3 of the C2, so it will correct the M1 power factor to 0.95. Okay, we look at this C2. Okay, so C2 was only have 3 steps only, 1, 2, 3. So that means when it switched to step 3 here, so that means the total unit use is 3 plus 2 plus 1. So that means total is 6 unit. Okay, 6 unit. So load for M1, okay, we have calculated just now. Load for M1 here, okay, load for M1, M2, and L1 here. Okay, so load for M1, so we simply take from here, and we analyze for power factor. For M1 is 0.78. So that means the initial is 0.78. So that means when we switch to step 3, so it increased from 0.78 to 0.95, as stated here, to 95. So that's why we know that this is the original power factor. This is the desired power factor. So seems like we have the K factor here, and the K factor, the tangent up cos 0.78 minus the tangent for the Q2 here, the targeted. Okay, so this is our P. So P multiply with the K factor. Okay, the K factor is 6.72 kVAR. Okay, what we require is 6.72 kVAR. And that means our system required 6.72. And what about the our capacitor? So because our capacitor voltage is different, our voltage is different, because our capacitor voltage is 440 as compared to the system voltage is 400. So that's why we need to do some modifications here. Okay, so in order to get 6.72 kVAR in the system, so we required 8.13 kVr for our capacitor, okay, for our capacitor. So that means the total unit, just now we have 6 units, so that's why we have total is 8.13, 8.13 kVr. So divide by 6, so that means we obtain the unit kVr is 1.35 kVr. Okay, and the third one is we analyze again the average power factor for this factory. So if this is the condition, C1 and C2 are switched to step 4 and step 2 respectively. C1 to step 4 and C2 is to step 2. Okay, so what is the C1 to step 4? C1 to step 4 mean we have how many units? 1 2 3 4 here. That means 2 plus 2 plus 1 plus 1 is 6 unit. And then C2 is to step 2 only. That means 2 plus 1 is 3 unit. That means 6 from C1, 3 from C2. Okay, so that means we have 6 unit for C1, 3 unit for C2. So 6 times this is per unit, per unit capacitor, and then we have the ratio of the voltage change, the voltage change, and then this is how much we get for our system. Okay, how much we get for our system, actual kVr that flow into the system. Okay, and then for the C2 also we have 3 units, and each unit is 1.355 that we obtain here. Okay, and then we compensate it with the voltage, the difference of the voltage. Then what we receive is 3.36, and that flowing into our system. I mean the total loads is 44 just now, and the total loads, how much is the total load here? 44. But since we have the capacitor bank or the power factor corrector, then we have to twist this one. That means the Q has been changed. The Q has been changed. So the Q original is 27. So now we minus, because we inject 6.97 from C1 and 3.36 from C2. So that's why we have compensate this much. Okay, so at the end this is our system. This is our from the TMB, for example, from the incoming, required from the incoming. So the incoming is only supply for 44 plus J17 only, instead of initially 27. Okay, so the dual power factor in this case is 0.93, like it. Okay, it's very simple. So if the C1 and C2, okay, accidentally switch to its maximum step, for example, so C1 and C2 is for the maximum step. So that means this is for step 6 and this is step 3. Okay, so that means in total we have how many? So 4 4 2 is 10, 10 13 14. So we have 14 units, and this one we have 6 units. Okay, so 14 unit for C1, okay, 14 unit for C1 and 6 unit for C2. So of course we need to compensate the voltage, the voltage difference. And then when we switch to the maximum steps, so the total Q injected to our system is 22.97. So again we can calculate 44 minus 20.65, okay, 0.65 plus this one. Okay, so we minus this one. Okay, we have to minus this one, and then finally we have this much. Okay, because it has been given here, L1 is disconnected. L1 is disconnected. So how much is the L1? L1 is the 10 kVr here. The L1 is disconnected. That means we need to deduct the L1. So L1 is this one, 20.65 plus J 10 kVr. Okay. So that means we need to deduct where is it? 20.65 for the P, and this one is for 10. So 10 is from the L1, and 22.97 is our corrector power factor, power factor corrector, C1 plus C2. So that's why in total we have now minus 5. It is not plus minus 17 like this one. So it's minus 1 is minus, that means we are overcorrected. We are overcorrected. That means our power factor now is in leading, in the leading, not in the lagging. So this is not healthy condition. So this is what we wanted to avoid. Okay, okay, that's all for the example 4.3 here. Then we continue a little bit more on the power factor corrector. So some issue in the power factor application is we try to avoid the nuisance trips caused by the power factor, because the power factor corrector, as we seen just now, we have several steps, and each steps, so it will have the switching transient. Okay? So the switching transient, so we can use the current limiting fuse to limit the capacitor currents. Okay? So it's to about 150 to 175%. See? And then for the capacitor discharge also, when we have the capacitor bank, we need to discharge it properly. Okay, we need to discharge it. How to discharge it? I mean, we discharge to a residual voltage of 50 volts 1 minute after it is disconnected. Okay, I mean, we need to discharge it up to minimum 50 volts. Okay? Sorry, maximum 50 volt only, and remaining residual voltage is mean remaining voltage at the capacitor. When we use the multimeter to check it, so the remaining voltage is 50 volt for the capacitor, and then it's safe. That means 1 minute after it is disconnected. So otherwise it will give spark and the sparking. So it's very dangerous, especially when you're dealing with the fuel, for example, is vaporized things, and then it will cause the fire. And in terms of the harmonic, of course, we need to avoid the resonance, because when we have the power capacitor bank, and in our system we have the impedance. The impedance consists of the X is the reactance, and the reactance, when these reactance in the system combine with the capacitance from the power factor corrector, then it might have the resonance. And I mean, we try to avoid the resonance. Either it is a series or parallel resonance. It's very dangerous. Okay, like this here, you have the series resonance. There is a series. The power factor is series in the equivalent circuit. It is in series with our transformer and cables here. Okay? And a parallel resonance is it is parallel. The capacitor cap here is parallel with the source impedance here. The source impedance including the utility here plus the transformer and the cables. So we try to avoid. Okay, how to see the harmonic? So when we plot the graph, we have the XL. Okay, we have the XL. So XL is the our system impedance and the reactance from our system, and then we plot the graph for the XC. So of course this is harmonics, or we can plot it using the frequency. That means we vary the frequency, because the reactance is the frequency dependence components. It's not like R. We no need to consider for the frequency, because it is not the frequency dependent component. But for the X, no matter is the XL or the XC, so it's depend on the frequency here, because we have 2 pi f. Okay? So that means when we vary the frequency along the way here, so we can plot for the XL for the system, and the blue color is the XC for the capacitor bank. So in between here, that means at the place where it is crossed here, is crossed here is the resonance. So in this case, it is resonant at near to the third order of the harmonics. Okay, third order of the harmonic here. So that means we need to have the so-called filter, the resonant filter, to filter out this one, and we divert it, let's say, to a little bit. So the when it near to the harmonic order, the third order harmonic, so this is not exactly at the third order harmonic. It's quite okay, it's safe, but when this point is near to either 1/3 or 4th or 5th or whatever, so it will give you the resonance. right? And then so what is the risk? What is the risk when you have this harmonic or the resonance? So of course, when the power factor corrector and the power factor corrections we measured in kVAR. So this kVAR, if it is greater than 25% of the transformer kVA, so let's say our transformer is rated at 1 MVA or 1000 kVA, 1000 kVA, and then our power factor is rated at 300 kVAR, and then you will have the high risk, high risk. When you have the resonance on that, so it will give you a high risk. I mean, as long as your power factor kVAR is more than 25% of the transformer kVA, then you will have the high risk on the resonance. Otherwise, if below than 15%, then it should be okay, no problems. Okay. About the harmonic also, the harmonic, so if the harmonic produced loads is greater than 40% of the transformer kVA, okay, so then it will give risk. So in this case, if it is below 25% of the harmonic producing load, then it should be okay. So how to calculate the harmonic? So this is H is the harmonic order, right? Harmonic order, third order, fifth order harmonic. So this is the H. H is equal to the square root of the kVA of the transformer divided by the Z transformer. So how much is the Z transformer? Multiply with the kVAR of our power factor corrector. Okay. So that means you can simply estimate how much is the resonance it might happen, okay, in this case. And of course, the capacitor switching transient is one of the headache things when you have the capacitor bank here. The capacitor bank is very normal, but we need to treat it properly. That means we need to de-energize our capacitor. Like just now, we have tried to de-energize the capacitor at least to 50 volts. That means at least for 1 minute, we discharge it. Okay. So this is the magnitude of the transient. That means it varied on two variables. Okay, the magnitude of the transient. And that means when you switch the capacitor bank from step 1, let's say, to steps 2, so it will have the transient. So this transient is depend on two variables. So what is that two variables? Is the one is the initial voltage at the capacitor bank, and that means before you switch. So how much is the initial voltage? And the second one is the instantaneous system voltage, because once you switch the capacitor bank, so it will flow into our system. So these are two main variables that we need to consider to minimize the transient during the switching of the power factor corrector. So one is the initial voltage, another one is what is the instant system voltage. Okay. So if this initial voltage of the capacitor and the system voltage have a very big gaps of the difference, that means we will have the trouble in terms of the switching transient. Okay. So the worst case is when you have the system voltage at peak voltage, and the trapped charge in the capacitor is at the opposite polarity. So it's opposite polarity, that means it will have a big gap. One is positive 400, another one is the negative 400, for example. So you have 800 of the difference. Okay? So this is the meaning, opposite polarity. And then this is the transient, the currents, the current. How we calculate? We can simply calculate it using the Vs. So Vs is the instantaneous just now, the variables, the system voltage, and Vc is the capacitor voltage. And then again we have the C, capacitor, and L is the inductor. Inductance is from our system. This is our system inductance, and then C is from the cap. That means you can simply calculate what is the magnitude of the current transient for this case. And then back-to-back capacitor switching. So this situation occurred when a second capacitor is switched on in close proximity to previously energized capacitor. That means in the previous you have the energized capacitor, and at the same time you also need to energize another capacitor. That means the second capacitor. So this is will cause the back-to-back capacitor switching. okay, back to back capacity, and it will amplify and the transient, so this is more dangerous. And a figure of, below here is the energization of the 50 kVr for the 80 volts of the capacitor switch steps with trap charge with 150 kVr of the other steps. That means you can see the difference. Okay? So this is the voltage and this is the currents, and the voltage and the current. So this is a huge transient happens, and huge transient happens when we have these two capacitor in that means it's energized. That means we try to minimize the capacitor's transient. So how to minimize the capacitor transient is we have two ways. The first one is we switch the capacitor at a point and in time when the system voltage matches the voltage. That means we try to minimize the difference between the voltage at the capacitor and the system. That means in terms of the polarity. And the second one, of course, we can this is more practical. We can insert some impedances. That means after we calculate, so we can insert some impedances, the reactance or the inductance in the circuit, so that we can minimize, or we can that means absorb some of the transient currents. So or the inrush current here. Try to minimize the voltage oscillation of that. Okay. I think I have finished for the part 1 for the chapter 4. Then we can continue in the part 2. Okay, so the part 1 has been finished, and I'll see you again in the part 2 for chapter 4. Thank you very much for your time.